For this problem, 2 point charges are placed on the y-axis. One is positive 3.0 times 10 to the negative 6 coulombs and located at position 0 meters, 2 meters. The other is negative 2.0 times 10 to the negative 6 coulombs and located at the origin, 0 meter, 0 meter. Use the diagram to find the magnitude and direction of the electric field and the force on a positive 1.0 times 10 to the negative 9th power coulomb test charge placed in the following locations. Location A, 0 meter, 1.0 meter. Location B, 0 meter, negative 2.0 meter. Location C, 1.0 meter, 0 meter. So the first thing that I'd recommend doing with this problem is setting up a scale using that coordinate system. So that way the negative 2.0 times 10 to the negative 6 coulomb point charge is located at the origin, that coordinate of 0 meters on the x-axis and 0 meters on the y-axis. 2 meters above that on the y-axis is the positive 3.0 times 10 to the negative 6 coulomb charge. And then we have the points A, B, and C at those three coordinates respectively. Other things I recommend doing, just to kind of make it a bit more clear what's happening, is use color coordination. By convention, a positive charge is typically going to be associated with a red color. So I highlighted the positive 3.0 times 10 to the negative 6 coulomb charge in the problem, and I shaded in the point charge. Now, one thing that we can notice for that point charge, instead of writing out in full scientific notation, I'm using that Greek letter mu in front of the unit coulomb. That is a prefix that is going to be the exact same thing as the scale of times 10 to the negative 6th power. It just allows us to have the full labeling on that positive point charge without having to write out the whole thing, but they're going to be used interchangeably. The negative point charge is going to be associated with blue, negative 2.0 microcoulombs. And then each of those three locations is where we would put a positive test charge. Now that positive test charge only has an exponent of 10 to the negative 9th power of coulombs. So that makes the charge on each of those three locations for the test charge only positive 1 nanocoulombs, which is going to be 3 orders of magnitude less charged than either of the 2 point charges. That is by design, because the test charge should have a positive charge, but not be large enough to alter the electric field that is being tested. That's why such a lightly charged object is going to be used. Now we're trying to find the magnitude and direction of the electric field and the electric force at each of those three locations. We can use Coulomb's law to figure out the electric force by taking one charge, multiplying by another charge, multiplying by Coulomb's constant, divided by the distance between those 2 points squared. Coulomb's constant being 9.00 times 10 to the positive 9th power, with units newtons times meter squared over coulomb squared. And then our electric field strength can be determined by taking that electric force, dividing it by the charge at that location. Now for this problem, we have 2 separate point charges and a test charge that will be placed at 3 locations. Because we want to figure out the electric field and the force at those 3 locations, we're actually going to be setting it up this way. For Coulomb's law, we're going to be using, for every single calculation, the charge of the test charge, and we'll be multiplying that by either the positive point charge or the negative point charge, as well as the distance between them. Because there are 2 point charges, each of those test charges at those 3 locations will have 2 force vectors from the electric force. That means we're going to actually need to end up adding them together to find the net electric force acting on the test charge at each of those 3 locations. So when we calculate the electric field, that's why it's going to be the sum of all of the electric forces divided by the test charge's charge. That means that we're going to have quite a few calculations, at least 16, in order to fully solve this problem. The 12 that are going to be really straightforward are going to be presented right now. Just to avoid overwhelming us, we're going to break this down location by location. So location A, we're going to first figure out the electric force from the positive point charge on the positive test charge located at location A. So we use Coulomb's law, where the first charge we're using, the positive 1.0 times 10 to the negative 9th coulombs, that is the charge of the test charge. We multiply that by the positive 3.0 times 10 to the negative 6 coulombs, that is the charge of the positive point charge. We multiply that by Coulomb's constant, and we divide that by the distance between those two charge points, which is 1 meter, and we square that. That will be 2.7 times 10 to the negative 5th power newtons, but I'm just going to be changing that a little bit to 27.0 times 10 to the negative 6 newtons. The reason for that is that way I can use that micro prefix, so that way on that force vector that I've attached to the location A, it's a downward force of 27 micronewtons. Once again, that just allows me to save space on my diagram. Now the reason why the force vector is pointing down is because the test charge and the point charge are both positive, so it will be a repulsion. So that arrow would be showing a repulsion for a positive test charge at location A. For the force electric on a test charge at location A by the negative point charge, we still use that positive 1 times 10 to the negative 9th coulomb for the charge of the test charge, but now we multiply it by the negative 2.0 times 10 to the minus 6 coulomb charge for the point charge. Still multiplied by Coulomb's constant, and we're still going to divide by the distance between those 2 points, which for this one also happens to be 1 meter, that we need to square. I did the same thing by making it not to the negative 5th power, but to make it to the negative 6th power. So the value I got was negative 18.0 times 10 to the negative 6th newtons of force, which, because that's an attractive force between these 2 points, also results in a downward forcing force vector of 18 micronewtons. For our sum of the forces, both of those two force vectors are pointing down. So I can just add their magnitudes together, which would result in 45 times 10 to the negative 6th power of newtons downwards. Now you might notice that for the two individual electric forces, one was positive and one was negative. That does not necessarily tell us the direction. It tells us attraction or repulsion. If you have a positive and a positive charge, or a negative and a negative charge, you'll end up with a positive value for your electric force. So positive in that case would be a repulsion. And if you have a positive and a negative, or a negative and a positive for the two charged objects you're looking at, opposites attract, so you would end up with a negative electric force. That's why I would recommend drawing the force diagram, the direction of the force vectors, and just using the magnitude. Assign the sign after you have the correct direction. That's why I would end up with, for my sum of the force acting on a test charge at location A, it's 45 micronewtons pointing downwards. To figure out the electric field strength there, we take that net electrostatic force of 45 times 10 to the negative 6 newtons and divide it by the charge of the test charge, giving us an electric field strength of 45,000 newtons per coulomb. I'll update that little data table that we have organizing our thoughts and move on to location B. Location B is 2 meters below the negative point charge, which makes it 4 meters away from the positive point charge. We calculate using Coulomb's law the same, but now instead of having that 27 times 10 to the negative 6 newtons of charge of force, it's only 1.69 times 10 to the negative 6 newtons of force. It's still a repulsion, which is why that force vector is still pointing down. Our electric force on a test charge at location B by the negative point charge, calculated using Coulomb's law, is negative 4.5 times 10 to the negative 6 newtons. It's an attractive force, but in this case, it's going to be an upward facing force vector. We have two force vectors here pointing in opposite directions. So when we add them together, we need to deliberately make one positive and one negative. For me, I'm saying up is positive, which is why that 4.5 times 10 to the negative 6 newtons, despite being calculated as negative using Coulomb's law, I'm deciding up is positive, which is why that's positive, and the other force was negative. When we add those two together, we ended up with 2.81 micronewtons of force pointing upwards. Dividing that by the charge of the test charge, we end up with 2,810 newtons per coulomb. Now, we can add that to our table, leaving us just with point C. Now for point C, we know that that is 1 meter on the x-axis. It's not up or down from the y-axis, so that's why the coordinate is 1 meter, 0 meters. To solve for the electric force that results from its interaction with the positive point charge, we need to know the distance between those 2 points, which is not given to us. However, we know that this shape could be a triangle, particularly seeing as we have an x and a y axis, so this is specifically a right triangle. We know the base there is 1 meter, we know the height is 2 meters. If we use Pythagorean theorem, a squared plus b squared equals c squared, we can end up solving for the hypotenuse, which would be the square root of 5 meters. Now I'm not going to simplify that down to some decimal number, because we're going to be plugging that into Coulomb's law, where that rad 5 ends up being squared anyways. So it would end up just square rooting to the squared, ends up with that denominator being 5 meters squared overall. But when I plug that into the calculator, I would end up with 5.40 times 10 to the negative 6 newtons. But that 5.4 micronewtons, still a repulsion, it's down and to the right. So far, for point A and point B, we've only had force vectors fall directly on the y-axis. We can also assume that the attractive force between a test charge at C and the negative point charge will be an attractive force on the x-axis. What that means is we're going to need to end up breaking up this electric force acting on a positive test charge at C by the positive point charge. We need to break that up into its horizontal and vertical components. But that means we need to know an angle, such as the angle that forms between the original force and the x-axis. We don't have enough information to solve for that, but we can use symmetry considerations to say that the angle we want to know is the same angle that forms between that 1 meter base and the hypotenuse in the triangle that we just solved for. We can end up using trig functions to try to figure out that angle. I'm just going to use the 2 meter side of the triangle that is opposite the angle I want, and the 1 meter side of the triangle that is adjacent to the angle I want, to allow me to use the tangent function. Tangent of an angle is the ratio between the length of the opposite side of the triangle and the adjacent side of the triangle. Calculators also have that function where we can do the inverse tangent of that ratio, and it'll give us the number of degrees that would result. In this case, the angle that we're solving for would be 63.43 degrees. That is going to be the angle that results between the original force and our x-axis. So if I redraw that triangle, make it a little bit bigger to see what we mean, it would look a little bit like this. For a new triangle, the hypotenuse would be that 5.4 micronewtons. We have that 63.43 degree angle between the hypotenuse and the x-axis component of that force. So the adjacent side of this triangle is the x-axis, the opposite side is the y-axis. So we're going to use more trigonometry to try to figure out the lengths of those two sides. If we're solving for the horizontal component, the x-axis component of the force, we'll need to use the cosine function, which is the ratio between the adjacent side and the hypotenuse. Because our horizontal component of force is the adjacent side, we can rearrange that to get the adjacent by itself, and we can calculate that by taking the hypotenuse, 5.4 micronewtons, and multiplying that by cosine of the angle. We would end up with having a horizontal component of force be 2.4 micronewtons to the right. We can do the same thing but with sine to figure out the vertical component, which would allow us to determine that the vertical component of tension, of the electrostatic force is going to be 4.8 micronewtons pointing downwards. Now I'm just going to redraw that just to kind of clear up this slide a little bit. So really what that would look like is after we calculate the original electric force that results from its interaction with the positive point charge, we have 2.4 micronewtons to the right and 4.8 micronewtons downwards. Our electric force that results from its interaction with the negative point charge, even easier, it's just the negative 19 times 10 to the negative 6 newtons again, but that's that attractive force to the left. figuring out our sum of the force here is not going to be as straightforward as just adding or subtracting these from each other. We're going to need to simplify this down to figure out the sum of the force x, the sum of the force y, and then combine those one last time. If we have 18 micronewtons to the left and 2.4 micronewtons to the left, overall, we end up with, acting on point C, 15.6 micronewtons pointing to the left. And we only had that one component of force pointing downwards, so we still have 4.8 micronewtons pointing downwards. To figure out how we can combine those, it'll just be another triangle calculation. And we can use that using Pythagorean theorem. So the resultant force, the sum of the force acting on a test charge at location C, would be 16.3 micronewtons. If we wanted to figure out the angle, we can just, once again, do inverse sine, inverse cosine, or inverse tangent, but that's not something we're going to need to focus on right now. So that's how we would end up solving for the sum of the force acting on a test charge at location C. Be a whole lot of trigonometry, but we got there. 16.3 times 10 to the negative 6 newtons, pointing down and to the left. As far as I'm concerned, that's as much detail as we need for exactly what the direction is going to be. Calculating the electric force, once again, just divide by the test charge, which in this case would allow us to have a field strength there of 16,300 newtons per coulomb. When we add that to our data table, that should wrap up all the information we need.